So today we are going to discuss about the dielectric properties and dielectric materials. See, if we see the materials can be classified in so many ways. So some of the ways is like this, based on the energy gap, based on the resistivity, and based on the valence electrons. Suppose if you take, for example, if you take energy gap, if the gap is large, more than 3 electron volts are equal to that one, those materials called insulating materials. The gap is overlaps, those materials are conducting materials. If the gap is very small, depends upon the type of the material, so those materials are called semiconducting materials. This is the one way of doing classification of material based on the resistivity. We'll see another way based on the valence electrons. In case of valence electrons, if the valence electron is less than 4, those materials are called insulating materials. If the valence electron is equal to 4, so those materials are called semiconducting materials. If the valence electron is more than 4 electron volts, those materials are called metals or conductors. This is how we are going to classify the materials. There are other also we can classify if you go for much deeper into the subject based on the behavior of the particles. Suppose for example, if you take a magnetic materials, the classification of magnetic materials can be done based on the magnetic dipole moments. The magnetic dipole is randomly oriented, those materials are called diamagnetic materials. The magnetic moments is aligned in a particular direction, those are called paramagnetic and ferromagnetic materials. So if you go much deeper into the subject, then we're talking about the behavior of the material. So, but in our case, we're talking about only dielectric materials. Suppose, for example, dielectric materials, all dielectric materials are insulators. So that means all insulators are not dielectric materials. Remember that one. So all dielectrics are insulators because there are no free electrons available for a conduction in dielectric. That means all electrons are tightly bound to the nucleus. That means all the electrons filled in those orbitals. Those are called insulating materials and also called dielectric materials. So what happens when these materials subjected to electric field? So when the dielectric material is placed in the electric field, the separation of positive and negative charges takes place in the dielectric, causing polarization of dielectric. That means, so whenever the dielectric material is going to place in the presence of applied field, there is a separation between the positive charge and negative charge that causes the polarization in the dielectric materials. Dielectrics are characterized by the polarization and dielectric constant. So these dielectrics are strongly frequency dependent and also temperature dependent. So due to the above facts, so dielectric constitute an important group of electrical and electronic engineering materials. That means, so whenever the dielectric material is placed in the applied electric field, that constitute electric and electronic properties. This is what you are going to study in this class. So like that, we can see the two different types of materials here. One is ferroelectricity and piezoelectricity are important properties exhibited by the dielectrics. This is little bit introduction about the dielectrics. So then what is a dielectric? Every material, take any material, is made up of atoms or molecules. Atom contains both negatively and positively charged particles. So these particles contain central as a nucleus or a positive ion. So in any material, atoms are arranged as a dipoles represented with a positive and negative charge. When these materials subjected to electric field, dipole moment takes place. So most important thing is what you want to make it is by application of electric field, you want to make a dipole moment in the dielectric material. That is most important property in dielectric materials. Suppose if you take a conductor material start conducting when electric field is applied, where you can see the conductivity. But in case of insulator, it opposes flow of electricity, does not have any free movement of electrons in the structure. But dielectric is a special type of insulator, does not conduct electricity, but it gets polarized when subject to electricity. That means most important thing differences between conductor, insulator and dielectric is dielectric is a special type of material. When subjected to the electric field, it causes dipole moment that in turn causes the polarization in the dielectric materials. This is what is a dielectrics. Now if you see this diagram, see, you can see this is a dipole. It is having a positive and negative charge. There are so many dipoles are arranged in a particular direction when the field is applied. So when the field is applied, what happens means in dielectric material, dipole moment gets arranged in the direction of applied field. So positive is moving towards the applied field direction and negative fields opposite to that applied direction. This is what going to happen in the dielectric materials when you subject it to electric fields. So this is polarization in a dielectric materials. Now if you come to types of dielectric materials, so how can you classify the materials of classify the dielectric materials? So dielectric materials can be classified based on the molecules present in the material. So there are two types of dielectrics. One is polar dielectrics, another one is non-polar dielectrics. So what is polar dielectrics? The polar dielectric is always having a permanent dipole moment exists in the polar dielectrics. That means positive and negative charge does not coincide. There is always having a distance between the positive and negative charge that causes the permanent dipole moment in polar dielectric materials. That's why it is called a asymmetric shape of the molecule. Asymmetric means is not a symmetrical, it is asymmetric. Distance between is always having some distance between the positive and negative charge. That is what is called a asymmetric shape of the molecules. So that's why dipole moments always exist in the polar dielectrics. See, for example, if you see this diagram, when the field is zero, this is what is called a dipole. There is a separation between the positive charge and negative charge that causes a permanent dipole moment. The permanent dipole moment exists even absence of electric field is zero. But on the whole, net dipole moment is zero because these all dipoles are randomly oriented when no field exists. Suppose if a field is applied, what happens means these all dipoles tends to direction of the applied direction. So that means positive charge move towards the field direction and opposite charge fields to the negative direction. That causes a dipole moment. Then net dipole moment is not zero in case of polar molecules when subjected to electric field. But individual dipole moment is not zero when equal to zero. When the field is not applied to the electric material, individual dipole moment is exist. But on the net dipole moment is always zero in the case of dielectric material. But when subjected to electric field, it undergoes polarization. That net dipole moment is not zero in the case of dielectric materials. So these are some examples of dielectric materials. That is water molecule, ammonia molecule, and HCl. There are so many materials are there. Next come to non-polar dielectrics. So in case of non-polar dielectric, the center of positive charge coincides with the center of negative charge. That's why there is no dipole moment in these materials. That's why it is called a symmetrical shape. See this diagram. So this is a positive charge coincided. That way dipole moment is zero. There is no separation between them because field is zero. If I apply the field, what happens? They get separated. They tend to separate it. Positive charge, negative charge. Then dipole moment is going to create on the application of applied electric field. It depends upon the strength of the field you're going to apply. In case of non-polar molecules, dipole moment is not zero on the application of applied electric field.
Sir, diagrams కనిపిస్తలేవు సార్.
Diagram కనిపిస్తలేవా?
లేదు సార్.
We are not getting screen, sir.
Screen also not coming. Oh, 1 minute, I will share it. Now it is coming.
Yes, sir.
No, sir.
Is it clear?
No, sir. Till it's not getting screen.
No, sir. Yes, sir.
Yes, sir.
Okay, I will start. I will resume the picture. Is it clear?
Sir, can you please tell once again?
From the beginning?
Yes, sir.
Yes, sir.
Okay, okay.
Yes, sir.
Okay, today we're going to discuss dielectric properties. So you know very well about these materials. You might have studied a certain level of extent in the lower classes. But in this class, we will know some idea. If we go much deeper into the dielectric materials, what it behaves, how it behaves, what are its properties, what are its applications, and how can you find out the electric field, all those things, and what is the meaning of polarization. These all things we will know it by you in this topic. Now, if we look at the background, how you can classify the materials, then can be done in so many ways. So broadly, you can classify the classification of materials based on the resistivity, based on the valence electrons, based on the energy gap. So you know very well energy gap, when the gap is very large, more than 3 electron volts are equal, so those materials are called insulating materials. The gap is very small, depends upon the type of the material, those materials are called semiconducting materials. The gap, no gap at all, those are called conducting materials. So if you go much deeper, you want to know it classification that can be done by behavior of atoms or molecules. You know very well how can you classify the magnetic materials. That is much deeper. It depends upon the classification can be the magnetic dipole moment, how dipole moment reacts, how it behaves. Based on that, we classify the magnetic materials. But when it comes to dielectric properties, dielectrics are all insulating materials. But all insulating materials are not dielectrics. Because insulating materials is nothing but there are no free electrons available in the valency band. That's why there is no conduction is going to take place in the case of dielectric materials. But you can see some electrical properties when these dielectric materials undergoes a subjection to electric field. That means when the electric field is up, when the dielectric is placed in electric field, separation of positive and negative charges takes place in the dielectric, causing polarization. That means the polarization phenomena plays most important role in case of dielectric materials. That means you have to make polarization in dielectric materials so that you can see the electrical properties. The dielectrics are characterized by polarization and dielectric constant. So these dielectric materials are always having strongly frequency dependence, and also some dielectric materials are temperature dependent also. So due to the above facts, dielectrics constitute an important group of electrical and electronic engineering materials. So these are the materials going to use in so many applications. Some of the materials are ferroelectric materials and piezoelectric materials. These are two important materials in case of dielectric materials. They are going to use in so many applications. Then what is a dielectric? Every material is made up of atoms or molecules. Atom consists of both negatively and positively charged, and these atoms are having a central nucleus that is a positive core. In many materials, atoms are arranged as a dipoles represented with a positive and negative charge. When these materials subjected to electric field, dipole moment is going to take place. The first thing is you have to make a dipole moment dielectric materials. That dipole moment causes a polarization in the dielectric materials. Suppose, for example, most of you know it, conductor starts conducting when the electric field is applied. But when electric field is applied in insulating material, it opposes the flow of electricity because it does not having any free electrons or free movement of electrons. But dielectrics are a special type of insulator. It does not conduct electricity, but it gets polarized when subjected to electricity. So this is what going to happen in the case of dielectric materials. Now if you go to next one, see this diagram. So in this diagram, so this is dipole. This is negative charge, positive charge separated by certain distance. This is one dipole. That's like so many dipoles you can see. So these dipoles are arranged in a particular order. When it is going to particular order means when you apply electric field. So whenever you apply electric field to any dielectric material, first it creates dipole moment. Then the dipole moment causes the polarization in the molecules. That means all the dipoles is going to move in the direction of applied field. But positive charge is always moves in the direction of the field direction, and negative charge is always opposes in the field direction. This is what going to happen in the dielectric materials. That is phenomena is called a polarization. So next we go for types of dielectric materials. The types of dielectric materials can be done based on type of molecules present in the material. So molecules in the sense can classify the polar dielectrics and non-polar dielectrics. So what is polar dielectrics? In the case of polar dielectrics, the positive charge and negative charge do not coincide. Do not coincide means there is always some distance between the positive charge and negative charges that causes a dipole moment. That means in those materials already dipole moment exists. That's why it is called a permanent dipole moment exists in the polar dielectrics. That means those the structure is like this asymmetric structure. There is no symmetry in structure available in case of polar molecules. But when these molecules, when these polar dielectric, when subjected to electric field, they undergo polarization. See this diagram. When E equal to 0, this is what is called a permanent dipole moment. Individually, they are having a dipole moment, but on the whole, if you consider total system, will consider net dipole moment is 0 because the dipole moment is cancel each other. So when the field is applied, so what happened means these dipoles align in the direction of applied field, then they undergoes the polarization. So net dipole moment is not 0 in when the polar molecule subjected to electric field. This is the polar dielectrics. Now you can see some example. Water is a polar dielectric. Ammonia is a polar dielectric. And HCl is hydrogen chloride is a polar dielectric. These are some examples of polar dielectrics. Now if you go for non-polar dielectrics. So in the non-polar dielectrics, the center of positive charge and negative charge coincides. Both positive charge and negative charge coincides. That means there is no distance between the positive charge and negative charge. That's why dipole moment is 0 in those materials. So these molecules are symmetrical in shape. So examples of non-polar dielectrics are hydrogen, nitrogen, oxygen, carbon dioxide. If you see this diagram, so this is what is called a positive charge and negative charge coincided. That means dipole moment is 0 when equal to 0. When the field is applied, what happens when the positive charge, negative charge gets separated, then it creates a dipole moment that causes a polarization in the non-polar molecules. This is about the non-polar molecules. Then you will see what is the difference between the polar molecules and non-polar molecules. First, we will see what is polar molecules. These molecules have a permanent dipole moment even in the absence of applied field. The polarization of polar molecules is highly temperature dependent. These molecules do not have a symmetrical structure. They do not have a center of symmetry. For this kind of molecules, there is absorption or emission in the infrared range. So you can see some example, lithium chloride and hydrogen chloride. So what is non-polar molecules? So these molecules do not have a permanent dipole moment. The polarization of non-polar molecules is temperature independent. These molecules have a symmetrical structure and they have center of symmetry. Center of symmetry means positive charge, negative charge coinciding. For these molecules, there is no absorption emission in the infrared range. These are the examples of non-polar molecules. Now we can see some examples of dielectric materials. So So dielectric materials can be seen in solids, liquids, gases, and vacuum. Solid dielectrics are highly used in electrical engineering. That means solid dielectrics plays most important role in engineering applications. Some of the examples of solid dielectrics are porcelain, ceramics, glass, paper, dry air, nitrogen, sulfur hexafluoride, and oxides of various metals are examples of gaseous dielectrics. Distilled water, transformer oil are common examples of liquid dielectrics. And what are the applications of dielectric materials? You can see some of the applications. These dielectrics are used energy storage in capacitors. These are the energy storage in capacitors. You know very well about this. And also can use to enhance the performance of a semiconducting device. That is, high permittivity of dielectric materials are used. Dielectrics are used in LCDs, liquid crystal displays. Ceramic dielectrics are used in dielectric resonating oscillators. You see some more examples. In electrical transformers, mineral oils are used as a liquid dielectrics. They assist in the cooling process. Castor oil is used in a high voltage capacitor to increase its capacitance value. Electrics is a special process dielectric that acts as an electrostatic equivalent to magnets. So these are some applications where it can use dielectric materials. Now we'll go for what is terminology. To understand complete behavior of dielectric material, you should know some terminology. What is electric dipole? What is dipole moment? What is dielectric constant? What is polarizability? And what is electric susceptibility? What is displacement vector? The electric dipole means there is separation between the positive charge and negative charge is nothing but an electric dipole. So if you go for dipole moment, product of magnitude of charge, product of magnitude of charge Q and distance between the two charges is called a dipole moment. That means it measures the overall polarity of the system. Dipole moments measure the total overall polarity of the system. That's why it is having mu equal to QD. Where mu is the dipole moment, Q is the charge, is the distance between the two opposite charges. Then what is dielectric constant? Dielectric constant is the ratio between the permittivity of the medium to the permittivity of free space. That's why it is epsilon r equal to epsilon by epsilon naught. So this is the formula for the dielectric constant. It is a ratio, that is, there is no units for the dielectric constant. What is polarizability? Let us consider an atom is placed inside the electric. The center of positive charge is displaced along the applied field direction, while center of negative charge is displaced in opposite directions. So whenever the placed dielectric material in the presence of electric field, there is a separation between the positive charge and negative charge is going to take place. So that causes a polarization in the dielectric materials. The process of producing, you can see here, the process of producing electric dipoles is called a polarization. So this, with the strength of electric field is increased. Suppose for example, if increase the applied field is more, it increases the strength of induced dipole moment also. That means mu proportional to E. The dipole moment is always proportional to applied electric field. More the applied field, more dipole moment is going to seen in the electric material. That's why mu equal to alpha E, where alpha is the proportionality constant, which is called polarizability. It can define, can put another way, we can define as a induced dipole moment per unit electric field. That is, induced dipole moment per unit electric field is called a polarizability. Next one is polarizing vector. Dipole moment per unit volume of the electric material is called a polarizing vector. Suppose if you take n number of atoms, n number of dipoles exist in the material, then you can measure it by using a polarizing vector, that is P equal to n mu, where n is the number of molecules per unit volume. So what is electric susceptibility? So in case of electric susceptibility, how easily a dielectric material can be polarized when subjected to an electric field, that can be measured by using electric susceptibility. So this quantity also determines the electric permeability of the material. polarizing vector proportional to applied electric field. So when the polarizing vector proportional to applied electric field is free proportional to E, then you can get the P equal to epsilon naught x, where x is the characteristics of every dielectric and which is called electrical susceptibility. So this is what is called electric susceptibility x equal to P by epsilon naught E. So if you simplify it, then you can get the electric susceptibility equal to epsilon naught. So this is about the electric susceptibility. So we'll go for displacement vector. So this is also called electric induction or electric flux density, the quantity which is used for analyzing electrostatic fields. Suppose, for example, if you want to analyze electrostatic fields in dielectric material, you should know what is displacement vector or electric flux density. Suppose, for example, if you take this equation, displacement is equal to Q by 4 pi r square, then E equal to Q by 4 pi epsilon r square. If this equation are equal, you can get the displacement vector D equal to epsilon E. But you know that the electric constant is epsilon by epsilon naught. Substitute in the above equation, you will get the epsilon or xc plus 1. Then you substitute this one, displacement in terms of polarizability, you also can get it. That will give the relation between the polarizing vector and electric field is the epsilon naught into epsilon r minus 1. This is about the displacement vector. Next, we will go for next topic is types of polarization. So you know very well how polarization is going to occur in dielectric materials. Whenever you apply electric field, it creates a dipoles that causes a polarization in the materials. Now, what are the different types of polarizations in dielectric? They are the formation of dipole moment, and there is orientation related to electric field. So polarization can be understood by the formation of dipole moment and how the dipole moment is going to behave in the application of electric field. That's the way you can classify the materials. That means depending upon the type of displaced charges causing polarization of the dielectric in the presence of the DC electric field, we have three types of polarizations. Actually, we're having four types, but as our syllabus, we're having only three. So first one is electronic polarization, ionic polarization, and orientation polarization. And fourth one is a space charge polarization. That is not you are having in your syllabus. Now we will take it one by one. What is electronic polarization and orientation polarization? So what is electronic polarization? See this diagram. This is positive charge. This positive charge is surrounded by an electron cloud. That means center of the positive charge, center of the negative charge is coincided when field is 0. Suppose when the field is applied, what happened means they get separated. The nucleus is going to move in the direction of the applied field direction and electron moves in the direction of applied field. So that process is called electronic polarization. The electronic polarization occurs in the presence of applied electric field. That's why mu proportional to E, where mu is the dipole moment, is proportional to the applied field strength. That is mu equal to alpha E, where alpha is the proportionality constant known as electronic polarizability. So electronic polarizability takes place in almost all dielectrics. Among all dielectrics, its response time is very quick. Response time very quick means as soon as you apply the electric field, within the milliseconds, it is going to respond to polarization. So that is what is called among all the dielectrics, its response time is very quick. Next, we will go for ionic polarization. So this ionic polarization occurs in ionic crystals only. For example, that is what is called sodium crystal. By influence of external field. See this diagram, no field is applied. No field is applied. So these are all having equidistance. They are going to maintain the equidistance. That means positive and negative charges is coincided. When the field is applied, this positive charge move towards the some position towards the negative charge, and this also move towards the negative charge, and also this is move towards the negative charge in the application of electric field. That is what is called ionic polarization. That also depends upon the applied field strength. Mu equal to mu proportional to E, mu equal to alpha IE, where alpha is the proportionality constant and it is known as the ionic polarization. And among all the dielectric, response time is very slow. It takes some time to respond. As soon as you apply the kinetic, what happens? It takes some time to act on that one. That's why it is called a response time is so next we will go for orientation polarization. Orientation polarization takes place only on polar dielectric. Going takes place only polar dielectrics, where permanent dipole moment exists in those materials. When the polar dielectric is subjected to fractional field, the molecule dipoles are oriented in direction of the field direction. This contribution of polarization of molecular dipole called a orientation polarization. So this is dipole. These all dipoles are randomly oriented when the field is 0. So as soon as the field is applied, all the dipoles align of applied field against direction of applied field that causes orientation polarization. That also depends upon the mu proportional to E and mu proportional to alpha naught E, where alpha naught is a proportionality constant known as a orientation polarization. Among all the dielectric, response time is very slow as compared to ionic, as compared to electronic dipole moments. Ionic polarization, an electronic polarization will have a independent of temperature. These materials does not depend upon the orientation polarization, strongly dependent temperature. Polarization is strong temperature dependent. Alpha E plus alpha I plus alpha 9. This is what is called total polarization can be achieved with some of the electronic polarization, ionic polarization, and orientation. Now you are seeing the electronic polarization, ionic polarization, and orientation polarization. Right now we'll see some expressions. That is what is derivation part. How, if you know the equation, we know very well. It depends upon what factors is going to. Right. So explain electronic polarization mechanics involved in dielectric materials. So electronic polarization, you know, this is a formula for induced dipole moment. So you can induce a dipole moment by application of applied electric field. So this is what is called alpha is called electronic polarizability. So this type of polarization is always, of course, in monoatomic gases exhibit this kind of polarization. So electronic polarizability is proportional to the volume of the atoms and is independent of temperature. Now we'll go for the equation. How you're going to calculate the electronic polarizability in dielectric materials. Let us consider a model of an atom. So the atoms are surrounded by a electron, that is nothing but electron cloud. So this is electron cloud, this is a nucleus. So first of all, you want to find out what is the charge density of the charged sphere. If you consider this is a sphere, so total, first of all, you want to find out the charge density of the charged sphere. So you know density formula, mass by volume. So so mass means you're not talking about mass here, we're talking about charge, total charge. This is charge of electron is multiplied by the atomic number, you will get the total charge of the electron. That is what is nothing but a mass. This is the volume of the sphere, 4 by 3 pi r cube. Now we'll get that charge density is called minus 3,4 by ZdV by pi r cube. This is nothing but equation 1. This is without field. So this equation I'm talking about without field. Now when the field is applied, what happens? The ions get separated, positive charge and negative charge get separated, in the presence of electric field, what happens? There are two phenomena occurs. So when now as soon as you apply electric field, there is always comes into picture Lorentz force due to electric field, which tends to separate the nucleus and electron cloud from the equilibrium positions. As soon as you apply the electric field, there is always disturbance is going to occur in the dielectric material from their equilibrium position. That is what is called Lorentz force. So once they get separated, one more force comes into picture. That is what is called a attractive Coulomb force arises between the nucleus and electron core. It tries to maintain the original equilibrium positions. That means one force is dragging, another force is opposing. So all the system is going to reach the equilibrium position. This is what going to happen when you apply electric field in the dielectric materials. Now we'll see, let's see the displacement made by the electron cloud from the positive core. Suppose see this diagram, you can understand very easily. So this is what is called a nucleus. So this is what is called an electron cloud. So nucleus is get displaced with respect to electron cloud at a distance of x. Field direction in this direction. This is what is called a displaced equilibrium position, and this is what is called nucleus. Then you can see the place ZE, that is nucleus, separated by distance x, and it is separated by with respect to electron cloud. This is what going to happen when you apply the field. So another thing you want to find out at equilibrium. What is equilibrium position? As soon as you apply electric field, Lorentz force is always equal to the Coulomb force. What is Lorentz force means? Charge is multiplied by the field. That is minus E capital E. That is already we have seen equation 1. Negative sign indicates the repulsive force. Now you'll find out the Coulomb force. Now you know the Lorentz force. Now you want to find out the Coulomb force. Charge is multiplied by the field. That is Z equal to Q by 4 pi epsilon naught x square. So you want to find out this total charge. Once you find out this total charge, when equal Lorentz force equal to Coulomb force at equilibrium position, you can find out the electronic polarizability in dielectric materials. To find out the total charge, first of all you want to find out the force. Force Coulomb force equal to charge into total negative charge enclosed in the sphere of radius x by 4 pi epsilon naught x square. So here total number of negative charge enclosed in the sphere of radius x. Considering the sphere of radius is x, charge density of electrons multiplied by the volume of the sphere. That means charge density you have already taken from the equation 1, and this is multiplied the volume of the sphere. Next, from that you will get the Q equal to minus ZE x cube by R cube. This is equation 4. Substitute equation 4 into equation 3, you will get the Coulomb force. That is ZE by 4 pi epsilon naught x square, and this is what is called a minus ZE x cube by R cube. Now we will get the equation 5. So this is the equation 5 is the Coulomb force. Now you know the already Lorentz force at equation 2. So at equilibrium what happened? Lorentz force is always equal to the Coulomb force. Then if we equate those two equations, we will get the displacement x 4 pi epsilon naught R cube E by ZE, that is equation 6. But when you see the displacement of electron cloud x is proportional to applied electric field, that causes a polarizability in case of dielectric material, that causes a dipole moment in the dielectric materials. So induced dipole moment is called magnitude of the charge. This is what is called magnitude, and displacement, that is what is called x. So if you compare those, substitute value of this x from equation 6, we will get the mu equal to ZB 4 pi epsilon naught R cube E by ZE. Then mu equal to 4 pi epsilon naught R cube E. So this is mu proportional to E, then mu equal to alpha E. If we compare these two equations, we will get alpha E equal to 4 pi epsilon naught R cube. Is called electronic polarization. What is called equation for the electronic polarization? The equation shows that this is the volume of the atom. R cube is too much volume of the atom. These are all constant values. That means electronic polarizability always depends upon the volume of the atom. This is how you are going to come to expression for electronic polarizability. Now we will find out relation between the alpha E and electric diode constant. So this is independent of temperature. That's why electronic polarization equal P equal to N mu E. So polarization equal to N alpha E. See what you can find out alpha, you can find out P by N E. So P, you know, epsilon naught into epsilon r minus 1. You can write alpha equal to epsilon naught into epsilon r minus 1. This is what is use the relation between the dielectric constant and electronic polarizability. So this is how we are going to derive the electronic polarizability in case of electric materials. Now we'll go for what is ionic polarization. How can you derive the expression for ionic polarization? Suppose, for example, if you take a sodium crystal, sodium ion is positive and chlorine is negative. When you feel there is no dipole movement, when the field is applied, what happens? Positive ion moves is shift. Negative shift at x2 distance. What will happen when the field is applied? Let us assume that there are one cation, one anion present in the each unit cell of ion. The electric field is applied. X1 and X2 which positive and negative ion move from their equilibrium positions. So resultant dipole moment per unit cell due to ionic displacement is given by induced dipole moment is called magnitude of the charge multiplied by displacement. Here mu I equal to E into x1 plus x2. We are talking about total displacement. Positive ion also is moving and also negative ion also moving. Total displacement becomes x1 plus x2. So total induced dipole moment becomes mu I equal to E into x1 plus x2. That is equation 1. When the field is applied, there is always having restoring force is going to take place in the case of ionic polarization because mass is more as compared to the electron. That's why we never spoke about the restoring force in electronic polarization. So restoring force comes into picture when the mass of the molecule is more as compared to other particles. For positive ion, restoring force F or F equal to beta 1 x1. This is what is called restoring force F equal to beta 1 x1. That is what is called equation 2. That is for the positive ion. Similarly, for negative ion, F equal to beta 2 x2. That is equation 3. So here beta 1, beta 2 are restoring force constant which depends upon the ions frequency of the molecule in which ions are present. M is the mass of the positive ion. Capital M is the mass of the negative ion. Then omega naught is the angular force. So what is reference to restoring force constant? Beta 1 equal to M omega beta equal to capital M omega naught square. That is equation 5. So omega naught is angular frequency. Substituting beta 1 into equation 2, the restoring force for a positive ion can be written as F equal to M omega naught square x1. So we know that force equal to E. That is equation 6 and equation 7. Equation 6 and equation 7 are equal. The restoring force is always equal to force. Then we get the x1 equal to E by M omega naught square. That is equation 8. Similarly, for negative ion, we can write x2 equal to E by M omega naught square. The adding equation 8 and 9 because you want to find out total displacement. That is x1 plus x2. Then get this equation. Find out the x1, x2 omega naught square multiplied by 1 by plus 1 by m. This is what is called an induced cause. Substituting equation 1 will get the mu by E square E by omega naught square 1 by m plus 1 by n. So where alpha is the ionic polarizability. So this is the final equation to get the ionic polarizability. That means ionic polarizability is inversely proportional to natural frequency of the ionic molecules and directly proportional to reduced mass given by 1 by m plus 1 by m. That is capital M. That is always inversely proportional directly proportional to reduced mass. These are the factors which influence the ionic polarizability. So next we will see the what is orientation polarization. So this type of polarization occurs in polar molecules where the polar molecules having a permanent dipole moment, even in the absence of applied electric field. And the field is not going to apply some kind of a permanent dipole moment, but net dipole moment is zero in case of those are materials. When the field is applied, that's just align in the direction of the applied field, then polarization is going to occur. When you see the equation, when the field is applied, the positive portion align along the direction of the field, the negative portion align in the opposite direction. This kind of orientation is called a orientation. Orientation depends upon the temperature. When the temperature is increased, the thermal energy tends to randomize the alignment. If you take a Langevin theory of paramagnetism, net independent become net systematic. This is what we call from the paramagnetism. This is equation depends upon the applied magnetic field. From the magnetic paramagnetic see the same particles can be applied application of electric field. Right, the polarization is like that is what is called the polarization. Then application of electric field. Same equation we're changing the magnetic field to the applied field. So this is what is called polarization is going to occur. Orientation polarization where n is the number of atoms. So that polarization not equal to n not e. That is what is called equation 1. So equation 1 equal to equation 2. We get alpha not equal to mu by 3 kBT. Is the proportion of temperature of the material. That's why ionic orientation polarization is always depends on the temperature of the material. That is inversely proportional. So that is how you expressions for the electronegativity and orientation polarization. Now we'll go to another important topic is internal field. We are going to find out the internal field when it is influenced by the electric field. Suppose, for example, when the dielectric material is kept in an electric field, it experiences a dipole moment. Whenever the dielectric material is kept in a external field, it experiences a dipole moment. Two things can happen due to the external electric field and due to the dipole moment. So, long range of Coulomb forces creating dipoles are called internal field or local field. This field is responsible for polarization of individual atoms or molecules. That means this internal field plays most important role, and also it is responsible for the polarizing of the individual atoms or molecules. So what happens when you place a dielectric in the presence of electron? If you see this diagram, so this is dielectric material. So inside the dielectric material, you are creating imaginary spherical cavity. This is imaginary spherical cavity. So once you create imaginary spherical cavity in case of dielectric material, this dielectric material is kept between the two parallel plate capacitors, and this is connected to the applied electric. This is connected to the applied electric. So whenever you place a dielectric material between the two parallel plate capacitors, and when you connect to the parallel plate capacitors, what happens means 4 types of electrons going to act at the center O. Dipole exists. One is called E1, E2, P, and E2. Even due to the applied external electric field, and U2 is the field which is going to develop inside the dielectric material, always opposes the applied electric field, and E3 is the induced surface charges on the spherical sphere. So this is the surface charges on the surface of the sphere, and E4 is the field inside the dipole charge. The spherical cavity radius is always more than the radius of the atom, so that more number of atoms, more number of dipoles can be occupied inside the spherical cavity. This is as shown in figure. So what happens? One is the field due to the charge on the plates that is externally applied. That is electric field due to the charges on the plates of a device. E1 equal to E by epsilon naught equal to E epsilon naught. E1 equal to E epsilon naught plus E by epsilon naught. E1 equal to E plus E by epsilon. These are the formulas you know. Displacement equal to, and also displacement in terms of polarization. These are the two formulas. By using these two formulas, we are finding out what is E1. E1 equal to E plus P by epsilon naught. This is about E1. When you come to E2, field due to polarization charges on the plane surface of the dielectric. This E2 is always opposes the applied field direction. E2 is always opposes the E1. That's why it is having E2 equal to minus T by epsilon naught. So hence charges induced due to the induced field. So the electric flux density D changes to electronic polarization. So E2 becomes minus T by epsilon naught. Now field due E3 is field due to the polarity charges is induced on the spherical surface. That is what you want to find out. This E3 is going to find out. Next, what is E4? Electric field due to the permanent dipoles of the atoms inside the spherical cavity is considered. Because we are considering electric field inside the spherical cavity, considered as a zero. Because we are considering dielectric material as a non-polar molecule. Because non-polar molecules is always having a center of symmetry. So electric field intensity at the center is zero due to symmetric structure. That's why taking E4 equal to 0. So equation 1, what is equation 1? E internal equal to E1 plus E2 plus E2 plus E3, right? E4. Then we can, the equation 1 becomes E internal equal to E plus E by epsilon naught minus P by epsilon naught plus E3. This goes cancel. Then E internal equal to E plus E3. Now you want to find out the E3. So to find out the E3, first of all, you want to find out the polarization. Now we'll see this diagram, figure 2. Let us consider a small area of ds. So this is what is called small area ds of a spherical cavity. This small area makes an angle d theta. So you can see the diagram, you can see small angle d theta here. See here. So theta is theta. Small spherical cavity, this is nothing but a ds, which is making angle d theta within angle t theta. That's what you are observing. That's what you are taking to for the further calculation. So, polarization P will be parallel to the applied field direction. That means polarization is also applied electric is always moving in the parallel directions. Then you can see the Pn is a component of polarization perpendicular to the area ds. So this is area ds. There you can see the perpendicular component of Pn. And Q dash is the charge on the area ds. Q dash is the charge on the area ds. Polarization is also defined as a surface charge per unit. That means this is Q by ds, surface charge per unit area. This unit area, this is surface charge. So polarization also can be defined as surface charge per unit area. That is Pn equal to P cos theta Q dash by ds, where Q dash is called P cos theta ds. So once you know the charge on the elemental area, spherical elemental area, now you can find out the electric field intensity. At the center, at the center C, due to charge Q is given by Q dash by 4 pi epsilon naught r square. That equal to P cos theta ds by 4 pi epsilon naught r square. The above intensity is along the radius r. calculating the intensity along the radius r. So what happens? The intensity is going to resolve into two components. One is parallel component, one is perpendicular component of electric field. Now we can see here. So this is perpendicular component. So this is parallel component. E is the parallel component. Y is the perpendicular component. The component parallel to field direction as shown in figure 3. Figure 3 is Ex equal to E cos theta. Substitute equation 3, substitute this equation 3 in equation 4, get Ex equal to P cos square theta ds by 4 pi epsilon naught r square. So this is the parallel component. Now we come to perpendicular component. The perpendicular component of field direction is always cancel each other. Means one component is in upward direction, one component is in the downward direction. These two are opposite each other. That's why perpendicular components is going to cancel each other. Yes, you are taking only parallel component are alone taken into consideration. Now you want to find out the total surface area of a ring. Suppose consider total surface area of a ring. Consider is a dA. It is obtained by revolving the ds about AB in the figure 1 as shown in figure 2. Equation 5 can be written as, so Ex equal to E3. So that's why this is a parallel component. In the present situation you are talking about E3, you want to find out ET. That's why I am making this equal to E3. E cos theta square dA by 4 pi epsilon naught r square. Equation 6. Now you want to find out the ring area. So how to find out the ring area? So ring area is called to circumference into thickness. You want to find out the circumference. The thickness you want the circumference equal to 2 pi y from the figure 2. From the figure 2 sin theta equal to y by r. So y equal to r sin theta. Y equal to r sin theta. Hence thickness is nothing but ds. That is what the surface area of a semicircle of elemental area. That is nothing but a r. We are taking the small r of ds. We know that from that we know that sector dt, that is the formula. Sector d theta equal to the angle equal to r by d. In our case r is ds. Substitute in that one. Then thickness becomes ds equal to r d theta. So what happens? Total surface area dA equal to circumference into thickness. We calculate circumference is 2 pi y. And also we calculate r d theta. Then you will get that 2 pi r square sin theta d theta, that is equation 7. Substitute equation 7 into equation 6. So equation 6 is nothing but E3. Already seen that one. E3 equal to P cos square theta dA by 4 pi epsilon r square multiplied by the 2 pi r square sin theta d theta. So E3 equal to, so we get a E3 equal to P cos theta sin theta theta by epsilon. This is nothing but equation 8. The charge present in the whole sphere. Now you calculated the electric field of a small elemental area in the form of a R. Now you want to find out the total sphere. How can you find out total sphere? By integrating the equation 8 between the limits 0 to pi. So if you integrate the equation 8 between the 0 to pi, you will get this value. E3 equal to P by epsilon naught multiplied by 2 by 3. So this value is 2 by 3. So we'll get a E3 equal to P by 3 epsilon naught. This is equation 9. Now substitute equation 9 into equation 2. What is equation 2? E internal equal to E plus E3. Now you calculated E3 from equation 9. Substitute in this, you get the E internal equal to E plus P by 3 epsilon naught. That is equation 10. So this is what is called a internal field or local field and also called Lorentz field. So this field plays most important to understand the behavior of polarization and dipole moment in electric materials. This equation 10 shows that E internal is different from the applied electric field. The local intensity E internal is larger than the macroscopic intensity E. That means applied electric field is nothing but a macroscopic intensity. The field which is going to develop inside the electric material is not a microscopic intensity. So molecules are more effectively polarized by application of internal electric field. Now finally, you can see what is Clausius-Mosati equation. The classical Mossack equation gives the relation between the dielectric constant and polarizability of a polarized dielectric. It is known as a Clausius-Mossack equation. Clausius-Mossack equation gives the relation between the dielectric constant and polarizability. That is, can be understood following equations. Mu proportional to E internal. When the field is applied, the internal field is going to develop, that causes a dipole moment. That is mu equal to alpha E internal, where alpha is the polarizability of the dielectric constant. If n is the number of atoms per unit volume of the dielectric, then polarization is given by P equal to n mu. So mu equal to n alpha E internal. Mu is substituted here, that becomes E internal. E internal from this equation, E internal equal to P by n alpha. Further, we know that displacement, already you know the equation epsilon E and displacement in terms of polarization, where P equal to epsilon minus epsilon naught E equal to P. E equal to P by epsilon minus epsilon naught. That is equation 2. So Lorentz field, just now we calculate internal field. E internal equal to E plus P by 3 epsilon naught. That is equation 3. So substitute equation 2, this equation into equation 3, will get E internal equal to P by epsilon minus epsilon naught plus P by 3 epsilon naught. If we simplify this one, we will get this equation. Then E internal, this equation becomes E internal field, that is equation 4. Compare equation 1 and equation 2. So equation 1 is nothing but P by n alpha. This is equation 4. If you compare, we will get the n alpha by 3 epsilon naught, epsilon minus epsilon naught, epsilon plus 2 epsilon naught. Then finally, you can get n alpha equal to 3 epsilon naught plus epsilon r minus 1 by epsilon r plus 2, where epsilon r is the epsilon by epsilon r. This is the Clausius-Mossack equation. So this is what is called polarizability. So this is what is called a dielectric constant. It gives the relation between the polarizability and dielectric constant. The above equation is Clausius-Mossack relation, which relates the dielectric constant of material and polarizability. Thus, it relates the macroscopic quantity dielectric constant with microscopic quantity polarizability. That means dielectric constant is the macroscopic quantity and polarizability is the microscopic quantity. Clausius-Mossack gives the relation between the macroscopic quantity of dielectric constant with the microscopic quantity of polarizability. So this is the main significance of the Clausius-Mossack equation. So I'll stop here.